In this video, I'll show you how to download and run Simulation IDE on your computer. First, open Google and search for Simulation IDE software. From the search results, click on the official Simulation IDE website. Once you're on the website, navigate to the Download section. Next, click on Official Releases. Now, click on the latest stable version available. After that, click on the drop-down menu and choose your operating system. Next, enter the amount you'd like to contribute. If you don't want to make a contribution right now, you can simply enter 0. Once you've done that, click on Download to start downloading the software. After the download is complete, open your Downloads folder. Now, extract the downloaded file using any file extraction software. When the extraction is finished, open the extracted folder. Inside the folder, locate the Simulation IDE application and double-click it to launch the software. This is how the Simulation IDE software looks after opening it. Now, let me give you a quick overview of the Simulation IDE interface. The Simulation IDE window is mainly divided into 3 sections. The first section is the Components and File Explorer panel. In this section, you'll find the Components tab, where you can access all the components available in Simulation IDE. You'll also find the File Explorer tab, which allows you to browse and access files and folders directly from within the software. For example, if you select File System, you can browse the different drives available on your computer. And if you select Examples, you can access a collection of pre-built example projects that you can open and experiment with. The second section is the Schematic editor. This area is where you'll create and simulate your electronic circuits. The Schematic editor is further divided into 3 parts. At the top, you'll find various controls and tools. In the middle, you'll find the main editor area where you'll design your circuits. And at the bottom, you'll find the console, which displays messages and information related to the simulation. The third section is the code editor. This section is used for writing and editing code for supported microcontrollers and projects. Just like the Schematic editor, the code editor is also divided into 3 parts. At the top, you'll find various controls and tools. In the middle, you'll find the code editing area. And at the bottom, you'll find the console, where messages, output, and other information are displayed. Now, let's see how to add components to the Schematic editor. Before we begin, if you'd like a larger workspace, you can resize the editor panels. Simply click and drag the edges of the editor panels, as shown in the video, to adjust their size. Now, let's create a new project. To do that, click on the New Circuit button. Next, to name the circuit, click on the button Save As. Enter a name for your circuit, and then click Save. Now you're ready to start adding components. From the Components section, select the component you want to use. Then simply drag and drop it onto the Schematic editor. To edit the properties of a component, first select the component, then right-click on it. Next, click on Properties. This will open the Properties window. Here, you'll find various settings that allow you to customize the selected component. If you want to change the default name of the component, locate the label field and enter the name of your choice. To display the label on the schematic, enable the corresponding option. In the next section, you can modify the component's values. Since we have selected a battery in this example, the available options are related to the battery. If you select a different component, you'll see options specific to that particular component. For the battery, adjust the voltage according to your requirements. If you'd like the voltage value to be displayed on the schematic, simply enable the corresponding option. For the resistance value, you can leave it at the default setting. Once you've finished making the changes, close the Properties window. To move a component, select it, and then drag and drop it to the desired location. To duplicate a component, first select the component. Then press Ctrl-C to copy it, and Ctrl-V to paste it. To delete a component, select it, and press the Delete key on your keyboard. If you need to rotate or flip a component, select the component and right-click on it. You'll find several options that allow you to rotate or flip the component as needed. Use whichever option best fits your circuit design. Now, repeat these steps to add and arrange all the components required for your schematic. Finally, to save your circuit, press Ctrl S on your keyboard or click the Save button. Next, let's see how to zoom in and out in Simulation IDE. To zoom in on the entire schematic, click on the Zoom In option in the toolbar. If you want to zoom out, simply click on the Zoom Out option, which is this one. You can also zoom in on a specific part. To do that, first select the component. Then click on this Zoom option to zoom in on the component. To zoom back out, click on the Zoom Out option again. Another quick way to zoom is by using your mouse wheel. First, move your cursor over the area where you want to zoom. Then scroll the mouse wheel forward to zoom in, or scroll the mouse wheel backward to zoom out. Now to pan the entire schematic, click and hold the mouse wheel button. Now drag the schematic editor as you need. This makes it easy to navigate around large schematics and focus on specific components. Next, let's see how to show or hide the grid in the editor. If you want to disable the grid lines, click on the Settings menu. Next, uncheck the option Draw Grid. The grid lines will immediately disappear from the editor. If you want to display the grid again later, simply return to the Settings menu and enable the Draw Grid option. Now, let's see how to connect components using wires. Creating connections in Simulation IDE is very simple. To start wiring, move your cursor over the pin from which you want to begin the connection. When the cursor changes to a plus sign, click on the pin. Next, drag the wire toward the destination pin. Once you reach the endpoint, click on that pin to complete the connection. Sometimes, while routing a wire, it may not follow the path you want, as shown in the video. If that happens, start creating the connection as usual. Then, whenever you want the wire to change direction, simply click at the point where you want to create a bend. After creating the bend, continue dragging the wire toward the destination and complete the connection. Using this method, complete your schematic. Now, let's see how to simulate the circuit. Once your circuit is ready, click on the Start Simulation button. The simulation will begin immediately. If your circuit contains a switch, turn it on to observe the circuit's behavior and see the results. At any time, if you want to temporarily pause the simulation, click on the Pause Simulation button. And to resume the simulation, click on the same button again. And if you want to completely stop the simulation, click on the Stop Simulation button. Now, let's see how to enable animated wires in Simulation IDE. If you want to visualize the flow of signals through your circuit, you can enable wire animations. To do that, click on the Settings icon. Next, go to the Circuits tab. Then enable the Animate option. Once enabled, the wires in your circuit will become animated during simulation. To view the animation, simply start the simulation as shown earlier in this tutorial. In the next section, we'll learn how to use the various meters available in Simulation IDE to measure and analyze circuit values during simulation. Now, let's learn how to use the probe component for simulation and circuit analysis. For this example, I have created a simple circuit consisting of a light and a variable voltage source. The voltage source is configured with a maximum voltage of 5 volts and a minimum voltage of 0 volts. To begin, locate the probe component and drag it onto the schematic editor. Next, double-click on the probe to open its properties. If you enable the Show Voltage option, the measured voltage will be displayed directly next to the probe in the editor. The next option is Threshold. The threshold value determines when the probe considers a signal to be in a high state or a low state. For example, in this case, the threshold voltage is set to 2.5 volts. This means that any voltage above 2.5 volts will be treated as a high state. Any voltage below 2.5 volts will be treated as a low state. When the probe detects a high state, it changes to an orange color, making it easy to identify active signals in your circuit. If you'd like to display the threshold value on the schematic, you can enable the corresponding option. Now, let's see how the probe works in practice. First, start the simulation. Next, click on the button to turn on the voltage source. Now adjust the knob to supply the desired voltage. After that, turn on the switch to power the circuit. To take a measurement, drag the probe to the point where you want to check the voltage. As you can see, the probe is measuring 2.41 volts. Since this value is below the current threshold voltage of 2.5 volts, the probe remains in the low state and does not turn orange. Now, let's change the threshold voltage and observe the result. Double-click on the probe to open its properties. Then set the threshold voltage to 2 volts. As soon as the new threshold is applied, the probe turns orange. This indicates that the measured voltage is now higher than the threshold voltage, and is therefore considered a high state. You can move the probe to different points in the circuit to measure voltages and check signal states, just as shown in the video. You can also place multiple probes throughout your circuit to monitor voltage levels and logic states at several locations simultaneously. A probe can also be very useful when working with circuits that have both positive and negative voltages. For this demonstration, I'm using a precision rectifier circuit that comes as one of the example circuits included with the software. In this example, the probe's threshold voltage has been set to 2.5 volts. Now, let's start the simulation. As I adjust the potentiometer, pay close attention to the probe's behavior. When the circuit produces a positive voltage, and that voltage rises above the positive threshold value, the probe changes to an orange color. This indicates that the signal is in a high state. Now, let's move in the opposite direction and allow the voltage to become negative. As the voltage drops below the negative threshold value, the probe changes to a blue color. This indicates that the signal is now in a low state. When the voltage remains between positive 2.5 volts and negative 2.5 volts, the probe stays gray. You can think of this as a middle state, where the signal is neither high nor low. To summarize, any voltage above plus 2.5 volts is considered a high state, and the probe turns orange. Any voltage between plus 2.49 volts and minus 2.49 volts is considered the middle state, and the probe remains gray. Any voltage below minus 2.5 volts is considered a low state, and the probe turns blue. This feature makes the probe especially useful when analyzing circuits that operate with both positive and negative voltage levels, allowing you to quickly identify the state of a signal during simulation. Next, let's learn how to use the voltmeter and ammeter in Simulation IDE. Before we begin, let's take a quick look at the pin connections. The red pin is the positive terminal. The black pin at the bottom is the negative terminal, and the black pin on the right side is the output pin for voltages. This output pin can be connected to components such as a probe or an oscilloscope for further analysis. For this example, I have created a simple circuit consisting of multiple LEDs connected in parallel and powered by a variable voltage source. The voltage source is configured with a minimum voltage of 0 volts and a maximum voltage of 5 volts. To see how the voltmeter and ammeter work, first start the simulation. Next, click on the button to turn on the voltage source. Now adjust the knob to set the desired voltage. After that, turn on the switch to power the circuit. As I begin turning on the LEDs one by one, notice what happens to the meter readings. The current reading on the ammeter changes as more LEDs are turned on. However, the voltage reading remains the same. This is because the LEDs are connected in parallel. In a parallel circuit, the current is divided among the branches, while the voltage remains the same across each branch. Now, I have modified the circuit by placing a voltmeter and an ammeter on each parallel branch. If you observe the readings, you'll notice that each branch has its own current values, and each LEDs have different voltage values across them. This allows you to see exactly how power is distributed throughout the circuit. Using voltmeters and ammeters in this way can help you better understand and analyze the behavior of your circuits during simulation. Finally, you may be wondering how to use the third pin available on the voltmeter and ammeter. To use it, simply connect a probe or an oscilloscope to that pin as shown in the video. This allows you to monitor and analyze the meter output using additional simulation tools. Next, let's learn how to use the frequency meter in Simulation IDE. For this example, I have created a simple amplifier circuit. The circuit includes a wave generator configured with the following settings. The waveform is set to sine wave. The frequency is set to 1 kHz. The phase shift is set to 0 degrees. And the quality is set to 100 steps. The circuit also includes a variable voltage source with a minimum voltage of 0 volts and a maximum voltage of 5 volts. Before starting the simulation, let's add the frequency meter to the circuit. The frequency meter has a single pin. Simply connect this pin to the point in the circuit where you want to measure the frequency. If you open the frequency meter's properties, you'll find an option called filter voltage. This setting allows you to filter out voltage changes below the specified value. In other words, any signal variation smaller than the filter voltage will be ignored by the meter. Now, place the frequency meter at the required measurement point. Once everything is ready, start the simulation. Next, click on the button to turn on the voltage source. Adjust the knob to supply the required voltage. Then, turn on the wave generator. As you can see, the frequency meter displays the frequency of the signal at the point where it is connected. This makes it a useful tool for measuring and verifying signal frequencies anywhere in your circuit during simulation. Next, let's learn how to use the oscilloscope in Simulation IDE. The oscilloscope in Simulation IDE comes with 4 input channels and an additional ground pin. Let's begin by exploring its settings. First, double-click on the oscilloscope to open its properties. The first 2 options allow you to adjust the size of the oscilloscope display. For example, if you change the size to 175 pixels, the oscilloscope screen becomes larger, making the waveforms easier to view. The next option is buffer size. This determines how many samples the oscilloscope stores in memory. A larger buffer allows you to retain more waveform data. Next is connect to ground. When this option is enabled, an impedance to ground is added to each input channel. Below that, you'll find the impedance setting. This value specifies the impedance connected to ground when the connect to ground option is enabled. Now, let's connect a wave generator to each of the 4 oscilloscope channels. Once everything is connected, start the simulation. Now turn on the wave generator one by one to view the waveform. Then click on Expand to access additional controls. At the top, you'll see buttons for Channel 1, Channel 2, Channel 3, Channel 4, and all. These buttons determine which channel the settings will affect. For example, if you select Channel 1, any changes you make here will only apply to Channel 1. Similarly, if you select all, the changes you make here will be applied to every channel simultaneously. Now, let's look at the controls available at the bottom. The first option is Filter. This filters out any voltage changes below the specified value. In other words, any signal variation smaller than the filter voltage will be ignored by the scope. The next option is Hide. This allows you to hide individual channels from the display. For example, if you don't want Channel 4 to appear on the screen, simply disable Channel 4 under the Hide option. You can also hide multiple channels at the same time. Next, let's look at the track setting. Before demonstrating this, let me hide all the channels. Now, notice the center line as I change the track's setting to Track 2. As you can see, the display is divided into 2 separate tracks. In this mode, the channels are assigned automatically. Channel 1 and 3 are placed on the top track. If I unhide Channel 1 and 3, they automatically appear on the upper track. Similarly, Channel 2 and 4 are assigned to the bottom track. If I unhide Channel 2 and 4, they appear on the lower track. If you select Track 1, all 4 channels are displayed on a single track. Switching back to Track 2 separates them as explained earlier. And if you select Track 4, each channel gets its own dedicated track. Now, let's see how the auto feature works. For auto to function properly, the simulation must be running. When you select a channel under auto, the oscilloscope automatically adjusts the waveform to fit the screen. For example, if I select Channel 1, the signal on Channel 1 is resized to fit perfectly within the display area. Next, let's understand the 4 adjustment knobs. The first knob is Time Division. This controls the horizontal time scale of the oscilloscope. In other words, it determines how much time is represented by each horizontal grid division. In this waveform, this one grid is equal to this time division value. The second knob is time position. This shifts the waveform left or right along the horizontal axis. It allows you to reposition the signal on the screen for easier analysis. The third knob is voltage division. This controls the vertical scale of the display. It determines how much voltage each vertical grid division represents. In this waveform, this one grid is equal to this voltage division value. The final knob is voltage position. This moves the waveform up or down on the screen. It helps you align signals, set a reference point, and prevent waveforms from going off-screen. Now, let's use these controls in a practical example. Suppose we want to calculate the frequency of this waveform. First, change the auto settings to all. Next, use the voltage position knob to center the waveform around the vertical reference line. You can either adjust it manually or enter a value of 0, depending on the waveform you're working with. Next, use the time position knob to align the waveform such that this point of the waveform starts at this point. Now, count the number of horizontal divisions that represent one complete cycle of the waveform. In this waveform, it is from here to here, which is 5 horizontal grid divisions. Now, multiply this number by the time division value, which is 200 microseconds. This gives you the total time period t of the waveform. In this case, t is 0.001. Using the frequency formula, substitute the time period value to calculate the frequency of the signal. For this waveform, the calculated frequency is 1000 Hz, which is equal to 1 kHz. Now, let's use the oscilloscope to measure the signal amplitude. Now, using time position knob, adjust the waveform such that one of the peak of a waveform is centrally aligned to the vertical line, like shown in the video. Also, use the voltage position knob to center the waveform around the horizontal reference line as I explained in the previous section. Now to calculate the peak amplitude, count the number of vertical divisions from the center reference line to the peak of the waveform, that is from here to here. In this example, the waveform spans approximately 5 vertical divisions. Now, multiply this value by the voltage division value. In this case, it is 500 millivolt, which will give you a peak amplitude of 2.5 volts. This is how the oscilloscope controls can be used to analyze signals during simulation. Finally, let's look at the trigger function. To explain the trigger function, I will be using this built-in example. Now, let's start the simulation and expand the oscilloscope. The trigger allows you to stabilize the waveform display using a selected channel as the reference. As you can see, the waveforms are continuously moving across the screen, which can make them difficult to analyze. To stabilize the display, simply select the channel under trigger function you want to use as the trigger source. For example, if you select channel 1 in the trigger section, the oscilloscope will use channel 1 as the reference point, causing the waveforms to appear stable on the screen. You can also define your own custom trigger reference point for a channel. To do that, first select the channel for which you want to create the custom reference point. For this example, I will select channel 1. Next, choose the same channel in the trigger function. Now, use the time position control knob to move the waveform until the desired reference point aligns with the vertical line. Once you've positioned the waveform exactly where you want, switch the trigger setting to all. Then, change the channel selection to all as well. From this point onward, whenever you select that same channel in the trigger function, the oscilloscope will use your custom reference point to stabilize the waveform display. This allows you to consistently align waveforms exactly where you want them, making it much easier to observe and analyze signal behavior during simulation. Before we finish the oscilloscope section, there's one final feature worth mentioning. You can assign your own custom names to the oscilloscope channels. To do that, simply click on the channel name field shown here. Then enter the name you want to use. This can be especially useful when working with multiple signals, as it makes it easier to identify each channel during analysis. Now, let's move on to the Logic Analyser. For this example, I have already added the Logic Analyser to the editor. The Logic Analyser in Simulation IDE provides 8 channels for monitoring digital signals. If you double-click on the Logic Analyser, its settings window will open. You'll notice that many of these settings are similar to those of the oscilloscope, which we covered in the previous section. Now, let's take a look at the additional options available. First, click on Export. Here, you'll find the base time setting. Base time refers to the smallest unit of time that the Logic Analyser uses when sampling digital signals, exporting data, or generating timing diagrams. The next option is Export at Pause. If this option is enabled, the Logic Analyser will automatically export the captured data as a VCD file whenever you pause the simulation. Now, click on Expand to access more controls. On the right side, you'll find the Time Division knob. This control adjusts the horizontal time base of the display, which we discussed earlier in the oscilloscope section. The next control is Time Position. This allows you to shift the displayed waveforms left or right along the x-axis, and this was also covered in the previous section. Next, we have the Bus option. This allows a channel to accept bus data. When bus mode is enabled for a channel, the corresponding pin changes to a green color. The next setting is Threshold Voltage, which is used to detect logic states and trigger conditions. There are 2 threshold values available. The first is the low to high threshold voltage, which determines when a signal transitions from a low state to a high state. The second is the high to low threshold voltage, which determines when a signal transitions from a high state back to a low state. Next, we have the trigger settings. Most of these options work in the same way as the trigger settings in the oscilloscope, which we covered earlier. However, there is one additional option that we haven't discussed yet. If you open the drop-down menu and select Condition, you can create your own custom trigger conditions. To define a condition, you first need to specify the channel name. For example, if you want to use channel 1, you should refer to it as shown in the video. Next, you need to specify the signal state. There are 4 available states: low, rising, high, and falling. When entering a condition, use only the first letter of the state. For example, if you want to trigger when channel 1 detects a rising edge, then enter the condition CH1R in the input field box. This tells the Logic Analyser to trigger whenever channel 1 transitions from low to high. You can also create more advanced logic expressions, such as the examples shown in the video. Finally, let's look at the Export option. Clicking this button allows you to export the captured data in VCD file format. These VCD files can then be opened in applications such as Pulse View for protocol decoding and more advanced signal analysis. Next, let's take a look at the code editor section of Simulation IDE. To demonstrate how it works, I have created a simple Arduino circuit on a new schematic page. In this circuit, an LED is connected to Arduino pin 6. Now, let's program this LED to blink. First, go to the schematic editor and click on Save As. Create a new folder for your project and give it an appropriate name. Once the folder has been created, open it. Next, enter a name for your schematic and click Save. Now, move to the code editor section. Click on the New button to create a new code file. Then click on Save As. Navigate to the folder that you created for this project. Enter a name for your sketch and save it with the .ino extension. You can now start writing your Arduino code in the editor. For this example, I have already written the code required to blink the LED. Once your code is ready, click on Save to save the sketch. Next, click on the Settings button. Then open the Compiler Settings option. Here, you need to set the toolpath to your Arduino IDE installation folder. In other words, browse to the location where the Arduino IDE is installed on your computer. For this feature to work, the Arduino IDE must already be installed. Similarly, if you're programming a PIC microcontroller, you should set the toolpath to a compiler that supports PIC devices. After configuring the toolpath, close the Settings window. Now, open Settings once again. This time, select File Settings. Next, click on the Compiler drop-down menu and choose the appropriate compiler. In this example, select Arduino. Once you've selected the compiler, close the Settings window. Now click on the Compile button to compile your program. Check the console at the bottom of the code editor. If there are no errors, click on the Upload button to upload the sketch. After the upload is complete, look at the bottom of the schematic editor. You should see the message, firmware successfully loaded. Finally, click on the Start Simulation button. As you can see, the LED starts blinking exactly as intended. And that's how you can use the code editor together with the schematic editor in Simulation IDE to write, compile, upload, and simulate your programs. Next, let's see how to use a hex file to simulate a programmable circuit in Simulation IDE. For this example, I have created an Arduino circuit with a push button connected to pin 2 and an LED connected to pin 5. I also have a hex file that is programmed to turn on the LED whenever the push button is pressed. Before proceeding, make sure that both the hex file and the schematic file are saved in the same folder. Once that's done, open Simulation IDE software. Now, drag and drop the .hex file into the code editor section. Next, click on the Upload button. If the firmware is loaded successfully, you'll see the message firmware successfully loaded at the bottom of the schematic editor. Now, click on the Start Simulation button. As you can see, when I press the push button, the LED turns on exactly as programmed. And that's how you can use a hex file in Simulation IDE to load precompiled firmware and simulate programmable circuits without writing or compiling the source code inside the editor. And that's it for this video. I hope you found this tutorial helpful. If you enjoyed this video, please don't forget to like, share, and subscribe to the channel for more tutorials like this. And if you have any questions or run into any problems while following along, feel free to leave a comment below. I'll do my best to help you out. Thanks again for watching, and I'll see you in the next video.